Welcome everyone. Good morning or good afternoon or good evening, depending on where you are located. Introducing myself, my name is Islam Mantawi, an assistant professor at Rowan University. I'll be moderating today's research seminar as part of the Education and Workforce Development and Technology Transfer activities at IBT ABC UTC. IBT ABC UTC is a university transportation center funded by USDOT to advance the frontiers of bridges, bridge engineering, bridge technologies, and ABC. Today's presentation is insight into the pull-off strength of polymer concrete and the effect of nanomodification. The seminar will be presented by Dr. Sharia Famganti, an assistant professor at University of Oklahoma. Along with Dr. Sharia, Ali Akbarpur, a PhD student at University of Oklahoma, will also present. We encourage all the attendees to ask their questions using the question box in the GoToMeeting. Before I hand the presentation to the presenters, I would like to thank Dr. Atorad Aziz-Namini, the director of IBT ABC UTC, for supporting this seminar. I would also like to thank Kathy Crowell, co-director of technology transfer at IBT ABC UTC, and Ankita Arvind, research assistant professor at the center, along with Dr. Ali Javed. I would like to thank Paul Lyles, who will be moderating the Q&A session, along with Rick Liptak. Paul Lyles is a former state bridge engineer at Georgia DOT. Rick Liptak is from Michigan DOT. Now, I will turn the presentation to Dr. Sharia for her presentation.
Good morning, everyone. It's good morning here, so thank you for being in this presentation where we would like to focus on the insights into the pull-off strength of polymer concrete and the effect of nanomodification. I would like to start by introducing our team here. We are from the University of Oklahoma and from the School of Civil Engineering and Environmental Science. Our lab is the Innovative Materials and Methods for Emerging Research in Structural Engineering. And we have quite a few students working here who have contributed to this data and also are currently working on extending the dissemination of this data into a journal paper. One of the students is my PhD student, Ali Akbarpur, and this is our structures department here with fantastic faculty, and I joined them in fall 2021. I'd like to run through the presentation, starting with a background and go through the hypotheses and objectives of this study. Ali will take over the materials and methods result and discussion and conclusions and future work. And I'd like to take a minute after that to thank our sponsors. Coming to this condition of infrastructure currently, we have 7.5% of bridges that are considered to be in a poor condition. And looking at the monetary aspect, a $22.7 billion value is needed annually to improve these conditions. So really the existing deterioration and preventative maintenance are the key priorities in our infrastructure outlook. But if you look at some of the most important chemical and physical factors that affect durability and strength, we have different attack of sulphate, levels of exposure through a sulphate kind of environment, alkali silica reactions, seawater effects, acid attacks, carbonation, clonal attack, and freeze-thaw effects. Our scope of the study today that we are sharing with you is regarding sulphate attack. Now, this work can be extended into the other durability aspects as well, but the current scope is looking at a sulphate attack point of view. What are the roles of polymer concretes in preservation treatments? If you look at the bridge deck, for example, bridge deck overlays. When polymer concretes are used as bridge deck overlays, they minimize penetration of water, oxygen, chlorides, and de-icing salts. They act as a protective barrier on top of the concrete bridge decks. And also they improve deck performance life and service life of the bridges overall, but the deck itself, it can be improved and the life can be improved. In preservation treatments, therefore, role of polymer concretes that are relevant, very relevant to accelerated bridge construction, which is the scope of our work. They have a rapid cure and lightweight characteristic. They minimize traffic disruption, all connected back to the rapid cure. Small thicknesses can be laid on to the existing substrates, and the dead load increase is very minimal. They are also wear resistant and skid resistant that make them very feasible for construction applications. We've talked about what is the role of polymer concretes, but I'd like to give a little bit of background about what is a polymer concrete. The polymeric resins are combined with curing agents or initiators, and silica or basalt aggregates are used to combine with those resins. Now, there are different kinds of polymeric resins. Some of the terms that you've already heard about. For example, epoxies and polyesters, vinyl esters are very, very popular polymeric resins. If you consider methyl methacrylate, it is one of biocompatible kind of polymeric resin, which is the scope of this study. The curing agent or the initiator is a methyl methacrylate powder that helps initiate that polymerization process and eventually hardening of the polymeric resin. And the silica or basalt aggregate is added for the strength parameter, a very fine aggregate considered here. The scope of this study talks about nanomodification. So what is nanomodification? And in polymer concretes, how does that happen? When nano-sized filler materials are added to polymer concrete, and I'm talking about a specific type of nanofiller, which is called carbon nanotube, they've shown to improve ductility, fracture toughness, and the polymerization process overall by creating a chemical cross-linking with the polymeric chains. If you see the left image here, it's a resin chain of epoxy combined with a functional group of carboxyl group, and the CNT is shown to have a chemical attack with the resin chain itself, and that creates a chemical bonding process. So with the improvements that carbon nanotubes have already shown through the polymer and polymer concretes, our scope currently includes carbon nanotubes for a nanomodification process. So what is our hypothesis and what are the objectives of the study? Because of the known mechanical effects and chemical changes on polymer systems, we hypothesize for this study that carbon nanotubes may improve bond performance of polymer concrete with the underlying concrete substrate. And the way we think that would happen because of past studies is because of chemical compounds and cross-linking agents that are suitable for adhesion and durability of polymer concrete overlay systems. So the objective of this study is we are assessing this performance through one ASTM standard test, which is a very prominently used test in bridges, which is the ASTM 1583 pull-off strength of polymer concrete. And we do that by incorporating carbon nanotubes in the polymer concrete, and we study this pull-off strength with the concrete substrate in two different conditions. One is a good condition where no exposure of any kind of chemical factors has happened. And the second condition being where the concrete substrate is exposed to sulphate attack and a sulfuric acid cell. And therefore, with these two conditions and conducting the pull-off strength tests, we report on the interface characteristics using the quantity data. So now I'd like to pass on to the student who's been working on these experiments. So Ali Akbarpur.
Yes, thank you very much, Dr. Vanwanti. Can you hear me?
Yes.
Okay, I will continue by, hello everyone, my name is Ali Akbarpur and I will continue by talking about some of the materials and methods that we use in this study. We use the pull-off test based on the ASTM 1583. In order to do that, we had to drill core into the concrete substrate and the overlay material at least 0.5 inches below the interface. The next step was to attaching the steel disc onto the overlay material using the epoxy adhesive. When the epoxy cured, we had to use the tensile loading device and using a coupling device to attach that to the steel disc, and then we applied the tensile load at a constant rate, approximately 5 psi per second. By dividing the tensile load to the area of the specimen, we could have obtained the bond or tensile strength of the specimen. Based on the ASTM 1583, there are 4 types of failure that can happen. If the failure happens at the concrete substrate or the overlay material, we can by dividing the tensile load to the area of the specimen, we can calculate the tensile strength of those materials. But if the failure happens at the interface of the concrete substrate and the overlay material, we can calculate the bond strength of the interface, which is our desired failure mode in this study. After doing some trial tests, we concluded that if we cast concrete substrate for 2.5 inches and then cast polymer concrete for 1 inch on top of that, and then drill cores 2 inches into the specimen, there is a high chance that the failure happens at the interface of the concrete substrate and the polymer concrete overlay. So in order to do that, we made a wooden molds, 8 by 8 by 3.5 inches wooden molds, and in the first step we cast a Portland cement concrete or the concrete substrate based on the mix design that you can see in this table. The next step was making the nano enhanced polymer concrete. In order to do that, the first step was to do the nanomaterial dispersion. In this study, we used 3 different types of carbon nanotube, 1 Pristine type and 2 functionalized type of carbon nanotube, COOH and ammonia, at 2 different amounts of 0.5% and 0.25% by weight. There were 3 steps to do the nano dispersion. The first step was to weigh the materials, and by the materials I mean different types of carbon nanotube and our resin, which was the MMA. Then we added the carbon nanotube to the MMA and put that under the magnetic stirring for 2 hours at the 800 RPM and 110 degrees Celsius, and we use the oil bath to hit the beaker, and we use the aluminum foil to trap the temperature inside the beaker. After the magnetic stirring was done, we put the beaker into the ultrasonication for 2 hours at the temperature of 60 degrees. Then we brought out the specimen and let it cool to the room temperature for more than 2 hours. And our resin containing carbon nanotube was ready to be mixed with the polymer concrete powder using this mix design that you can see in the table. And we can cast the polymer concrete overlay on top of the concrete substrate. Before casting polymer concrete overlay onto the concrete substrate, we had to do the surface preparation. We had to follow the CSP between 5 to 9 for the polymer concrete overlays, and we used the ICRI recommendation, and we used the adhesive water jetting and abrasive for grinding on the surface of the concrete substrate. After that, we cast polymer concrete on top of the concrete substrate. You can see the before and after picture of the concrete substrate and the polymer concrete overlay in these figures. And after that, we had to drill cores onto our specimen. As I mentioned earlier, we made 2 inches cores into our specimen using the universal drilling machine. Then we attached a steel disc on top of the specimen using the epoxy. It took 3 days for the epoxy to cure, and after that, the specimen was ready to perform the pull-off test based on the ASTM 1583 using the HydroJAS 2000. And also to understand the effects of one of the chemical and physical factors that can affect the durability of specimens, we made a sulphate chamber to simulate the sulphate attack. We used sodium sulphate to prepare the container. The mass fraction of the salt was 6%. Also, in order to maintain the pH equal to 3, we used sulfuric acid. We subjected our specimens to the sulfate environment for 210 days. You can see the specimens after 28 days, 140 days, and 210 days. And also you can see the produced ettringite after the 210 days. After bringing out the specimen after 210 days, we did the surface preparation and we cast a nano-enhanced polymer concrete on top of that. We made the cores and attached the steel discs to perform the pull-off test. Now I will continue by providing and discussing some of the obtained results. We did the unconfined compression test based on the ASTM 339 and ASTM C1579. You can see the compressive strength of the concrete substrate was around 9,700, and the unconfined compression strength of the polymer concrete was 8,700. You can see they are showing a similar compressive strength. And also we did the MOR, the modulus of rupture test on our specimen. You can see that the MOR of the concrete substrate was around 1,100, and the MOR of the polymer concrete was around 3,400. You can see that the MOR of polymer concrete was higher than a Portland cement concrete, 3 times the concrete substrate. And also, in order to understand that our dispersion happened well and we have a homogeneous carbon nanotube dispersion into our resin and into our polymer concrete, we did some tests. You can see the dispersion stabilization picture after 48 hours. You can see the carbon nanotubes have been dispersed very well into the resin, and also you can see the polymer concrete containing carbon nanotube and neat polymer concrete in these pictures. The black one is the polymer concrete containing carbon nanotube into the unconfined compression test. And also you can see the microscopic picture of these specimens at the bottom of the slide. These black dots show the carbon nanotubes, and you can see the dispersion happened homogeneously throughout our polymer concrete. As I mentioned earlier, there are 4 different types of failure that can happen while doing the pull-off test based on ASTM 1583. You can see the failure at the concrete substrate in this figure. You can see the failure at the interface of the concrete substrate and the polymer concrete overlay in this figure, and you can see the failure on the at the polymer concrete in this figure. And also there is one another failure mode, which is failure at the steel disc. Now I will continue by showing you the specimens after performing the pull-off test. As I mentioned earlier, we used 3 different types of carbon nanotube at 2 different percentages by weight, and we compared them to the neat polymer concrete. As you can see, 0.25% of carbon nanotube pristine you can see the failure mode that happened at the interface. Actually, I should mention that we eliminate the data or the specimens that were detached at the steel disc, and you can see the failure modes that happen either in the concrete substrate or in the interface or the polymer concrete overlay. You can see the pristine 0.5%, 2 of the specimens fail at the interface. You can see the 0.25% COH and 0.5% COH in this figure, and in the figures on the right, you can see the specimens, ammonia specimens. In this figure, you can see the pull-off strength result of all the tested specimens. You can see the 6 different types of polymer concrete with carbon nanotube, and we compare them to the neat polymer concrete. Each type of specimen have 2 different bars. The inclined bars, the bars that have inclined lines in them, show the average strength of all tested specimens. As you can see, the neat specimen showed higher pull-off strength in comparison with the nano-modified ones. And you can see the bars with the straight lines. In order to kind of draw those bars, we use 2 different assumptions. One, in order to draw these bars, we use the data of the specimens that was only failed at the interface of the concrete substrate and the polymer concrete overlay. And also, based on the transport data sheet, we should have used the polymer concrete should have at least 250 psi as the pull-off strength. So we use these 2 different assumptions to draw the second bar of each type. And as you can see, the 0.5% COH demonstrated the similar pull-off strength to the neat polymer concrete. Also, 0.25% and 0.5% of a pristine type of carbon nanotube didn't show any pull-off strength, and it was negligible. Now I will continue by presenting some of the obtained data of the pull-off test on the unhealthy substrate, which was in contact with the sulphate ions. You can see the failure in the polymer concrete and interface and the concrete substrate in these figures. Since the pristine type of carbon nanotube didn't show any pull-off strengths, we eliminated that from the test matrix for the unhealthy substrate. And as you can see, we used 2 different functionalized type of carbon nanotube and at 2 different percentages by weight. Now you can see the all 5 tested 0.25% COH specimens were failed at the interface. 3 of them of the specimens at 0.5% COH failed at the interface, and 2 of them failed at the steel disc detachment of the steel disc specimen. And you can see the ammonia specimens on the right. Now I will continue by discussing some of the obtained data from the pull-off strength of the specimens having unhealthy substrate. 0.25% pristine and 0.5% pristine didn't tested. The 0.25% COH didn't show any pull-off strength that was negligible. And as you can see, again, for bars that have inclined lines, they are all the specimens, and for the bars that have straight lines, they are the specimens that have been failed at the interface and also have an pull-off strength more than 250 psi. As you can see, the neat polymer concrete showed a higher pull-off strength. 0.5% COH showed higher pull-off strength in comparison to the neat polymer concrete and all of the others. And also for 0.25% and 0.5% NH2, we didn't have the results that at least 2 of the specimens were, the pull-off strength of the 2 of the specimens were higher at the more than 250 psi. In this figure, you can see the comparison of the pull-off strength of the neat polymer concrete, which had the healthy substrate and unhealthy substrate. As you can see, when we had the unhealthy substrate, the pull-off strength decreased. Also, you can see in these 2 bars, you can see the comparison between the healthy and unhealthy substrate, while with having the 0.5% COH polymer concrete on top of that. As you can see, unhealthy substrate showed lower pull-off strength. And in comparison with when we are having the deteriorated or unhealthy substrate, using the 0.5% carbon nanotube, 0.5% COH carbon nanotube increased the pull-off strength by 15%. And it shows that if we use these type of functionalized carbon nanotube, we can have a higher pull-off strength in unhealthy situation. And also, you can see the interface of pull-off using the keyends we use. You can see the microscopic images that we took from the interface of our neat and 0.5% COH specimen on the unhealthy and healthy situation. You can also see the concrete substrate which has been attached to the polymer concrete overlay in these figures. Now I will conclude our presentation by providing some of the conclusion. This work investigate for the first time the pull-off strength of the nano-modified polymer concrete. As you can see by the obtained result, the polymer concrete has a tensile strength at least three times of the concrete. 0.5% COH functionalized type of carbon nanotube showed similar pull-off strengths as neat polymer concrete in the kind of healthy situation, and while proposing other benefits such as the ductility, improved fracture toughness, and chemical effects. And also a polymer concrete containing 0.5% COH demonstrated 15% increase in pull-off strength when we're having the unhealthy substrate or the substrate which was exposed to this sulphate environment. And as you can see, as I mentioned earlier in the microscopic images, you can see the surface damage of the concrete due to the sulphate exposure. And for the future work, there is you can kind of investigate the cost analysis and the effects of chemical and physical factors, other chemical and physical factors on the pull-off strengths of these materials.
I would like to take a minute here to really thank our sponsoring agencies. Of course, to start with the Accelerated Bridge Construction, the UTC at FIU. Extremely thankful and grateful for their funding to make this work possible. All the materials that were used in the study for the polymer concrete was donated by Transpo Industries. The other funding agencies that we are working currently are listed below. Some of them are partnering agencies for material donations specifically. We have another exciting project coming up, which has just been awarded from the ACI Center of Excellence for Non-Metallic Building Materials, which is ACI NEX, the last logo here on the right. The NEX is interested in getting some polymer concrete guidelines and specifications, and we are partnering with ACI 548 committee, which is for the polymer concrete in ACI, and I'm a member of that committee, and we're working with them and the ICC evaluation service to get these guidelines in place. So the data from this study will also be considered in making these guidelines, because how nanofillers can improve polymer concrete's properties is growing research, and we're happy to be contributing to that particular science. With this, we conclude our presentation and open the floor for questions. Thank you.
Thank you, Sharia, for a great presentation. Now I will hand this part of the seminar to Paul to actually moderate the Q&A session. Paul?
Okay, thank you. I am, and Shira and Ali. We do have a couple of questions that have come in, and we should have some more that come in when we get underway. But let me go ahead and we'll ask some questions. And the first one we have, this came in pre-webinar, and it says, does time of placement, that's the deck age, significantly affect pull-off strength? And then another, go ahead and answer that one.
So yes, the time of placement does affect the pull-off strength, because if you consider it, what kind of failure is seen is governed by the different strengths, right? You have the overlay, you have the interface, and you have the substrate. So if the substrate is weak, you will see lower strengths, and you might see a failure more in the substrate than in the overlay or the interface. Now, in practice, the type of failure mode that you'd like to see is in the substrate. You want the bond for the overlay and the concrete to be strong enough, and that value is that 250 psi strength.
Okay, now another part of that question was, does the presence of chlorides after winter temperatures significantly affect the pull-off strength?
So if there is seeping of those chlorides into the concrete, yes, of course, that weakens the substrate itself, and that's what we are trying to actually focus on this study. We showed how penetration of sulphate ions, not chloride particularly, but sulphate ions, how they can affect the concrete itself and the bond with the concrete. So as you can see, the bond significantly reduced with an unhealthy concrete, which had that penetration of those ions. So yes, there will be significant changes. But I must say one thing, the guidelines of the overlay itself says that there should be a certain specific strength of the underlying substrate in order for the overlay to actually bond well. So if there are patches where there is not enough strength developed with the substrate, then definitely the engineer should be reached out to and see maybe some other kinds of solutions. How maybe if, let's say, it's a good enough depth for the substrate, and maybe the top part can be removed, maybe like an inch or two from the surface can be removed and repaired, and then the overlay can be applied. So that can be possible options.
Okay, another question that came in beforehand was, why did you choose a methacrylate-based material for your study?
Well, that's a great question. You saw a lot of resins that I showed before for the usage of polymer concretes, but our focus was on accelerated bridge construction, and methyl methacrylates have shown to have a quicker setting time than epoxy. So that was solely the reason. We wanted something that had a quicker setting time and very related to the accelerated bridge construction goals, right? To have minimal traffic disruptions, lay quickly, and don't have road closure for a long time. So those were really the idea for using MMAs.
Okay. Another question that came in beforehand, this is, what are the potential health risks of working with nanoparticles and methacrylate?
Sure. So I have to take a two-part way to answer this question. Let's come to the methyl methacrylates. So MMAs are actually also used, I don't know if a lot of them know it, but also in dental prosthetics and also in bone cements. So they are biocompatible, that is what is said for the methyl methacrylates. They are slightly soluble in water also. Acetones and other kinds of chemicals can have a good, the MMA can be soluble in these kinds of chemicals, but for water, they're slightly soluble. So having said this, though, when the mixing process is happening, when the MMA is becoming PMMA, which is polymerized MMA, we would like to take some kinds of safety measures like we do for other kinds of chemicals as well, like typical kind of mask, and if there is enough ventilation in the project site during mixing and placement, then it is very much more feasible. But if there's no ventilation or there is limited flow of air, then a respirator is something that is suggested for the usage of MMAs. Now, the second part of the question had CNTs. So carbon nanotubes, if I look at just the structure, if you look at it, they're very, very small materials. We are talking about each single CNT having a length of about 15 micron and a diameter of about 13 nanometer. So we're talking about tiny particles if you take a single nanoparticle. So they are potentially flying and become aerosols if not properly mixed. So during mixing, it's suggested to have some kind of PPE in place to carry on with the mixture. But after mixing, the CNTs have no kind of flying nature because they are already in the resin. And if it's functionalized carbon nanotubes, they are potentially making that chemical bond with the resin itself. So after mixing, no potential risk. Before mixing, PPE needs to be used to prevent any kinds of aerosols getting into respiratory systems.
Okay. We have a question here. We'll get into new questions now, but the first one was, why did you test for sulphate effects instead of maybe chlorides in your research?
Sure. I do want to point out that my PhD student had his master's in this area of sulfate ions, and he knows how the expansion of the concrete can work. He knows if the pH levels are okay for the cell. So using his experienced database, we wanted to first touch on one of the chemical factors. We cannot be doing all of them together. That's not the scope of the study too. With the timeline and the budget. So we touched on one of the chemical factors, which is sulfate. And also, if you look at the ettringite formation, there was one picture, beautiful picture that we had ettringite, the expansion result in the ettringite coming out. Surface preparation for overlays can be very tricky in these aspects. So we studied sulfate attack for now. I'm really hopeful that we can extend into the other chemical factors as well.
Okay. We'll get some other questions here that came in, and this goes along with that. It says about, do you expect similar results with concrete contaminated with chlorides?
I cannot comment on what kind of results we can expect. I don't want to get into that, but I can say that because of the results we've seen now with the sulfate attack, maybe a larger database also can solidify this. But seeing that a weaker substrate still was able to bond well with the nanomodified, it may be possible that chloride ion penetration, if it has similar effects for the concrete, can potentially show us some improvement. But I don't want to predict the outcomes before we do even one single test.
Yeah. Okay. Did you investigate the effect of temperature on the bonding of the polymer to the concrete?
So that is a great question. We've had in the entirety of the project, we've had several seasons that went in and out, right? We had cold temperatures and heated temperatures. So we want to say that this particular polymer concrete does not work well beyond a temperature of 90 F. So the storage and application is not recommended beyond 90 F. So that is my conclusion.
Okay. Is the polymer totally inert to different chemical environmental aggression?
No, it's not. I would need some more data to completely comment on that. But for now, there is very limited database available in literature too about what the different environments this polymer can survive in. So I don't want to comment saying yes, it's absolutely fine. But for the sulfate itself, what we've seen, I can comment on that, and we were okay with that. So other chemical factors, I am unsure of that.
Okay. I had another question here on when you're testing the thing, there's no cyclic loading or anything like that involved. We've seen overlays that'll scale off in the wheel pass. We were just wanting you to comment on that.
So polymer, the particular test we were talking about, ASTM 1583, is conducted after the polymer overlay has cured on the substrate. It's not specifically under a load, but after the deck has experienced some load, if you want to repeat the polymer pull-off test, and then the results vary, then that is something to consult the engineer as well, to look into whether the loading cycles or the intensity of loading has any kind of impact on the bond strength itself.
Okay. And then I was a little bit curious on the environmental chambers and stuff. They have some pretty sophisticated things in research now, where they'll do freeze-thaw cycles with fog mists and even loading sometimes. I was just curious your thoughts on that.
Yeah, definitely. We have a very good freeze-thaw chamber here in OU that we use for other tests. One of the tests right now that we're investigating is another ABC UTC and an SPTC related project. So if so that particular chamber we can get to -30 to +30, so it runs one cycle. About seven cycles in a week, I think, somewhat like that, because external temperature also kind of affects those cycles. So there are a lot more sophisticated equipment, but if we have to look into freeze-thaw effect for this same scope, we definitely start there.
Okay, I think that's most of the questions now. Rick, do you want to come on if we have any left, or you may have some questions?
Yeah, so I think you've hit on all the questions, Paul, which is great. One question that you mentioned with the temperature during the application, obviously there's a high end, but the one of the things we faced here in Michigan, we have a limited window to do the work, and we end up with a low temperature, you know, and with moisture, because that low temperature, there's always a little bit of moisture on the surface, and we've got to wait till the temperature comes up. Did you see anything, or, you know, is there any, I guess, stuff that you'll be looking at relative to that with the lower end and the moisture of the?
So that particular aspect affected our adhesive, which bonded the steel tensile loading device to the polymer concrete. So epoxy was used in order to bond that steel device, which was used for the pull-off. And epoxy does not perform well in those low temperatures. So we redid the epoxy application by subjecting it to heat, because in heat itself, it takes 1 day to completely cure. And without that external heat in regular room temperatures, it takes 3 days to completely cure. So below those temperatures,
Because we're constantly, it seems like, fighting with contractors that, you know, when they want to do some of this stuff and they're trying to push the lower limit because of the time frame. But that's good to know. Thank you. So I think with that, we're pretty much we got all the questions answered, and you did a great job with the presentation, good and informative. And I guess we'll turn it back over to Islam, and you can close this out. So, okay, thanks.
Okay, thank you, everyone. Thank you, Shreyas. Thanks, Ali. Thanks, Paul, and for moderating the Q&A session. And for now, before we adjourn, I would like to show some slides related to the next monthly webinar, which is different than the research seminar. So the next monthly webinar will be on Thursday, May 16, 2024. It's going to be the regular time, which is 1 p.m. to 2:15 p.m. Eastern Time. You will receive certificate of attendance. And the title of the presentation is Condition Assessment of In-Service Bridge Cables Using Innovative PTC Methods. And the presenter is Khalid Mahmoud. He is a Chief Bridge Engineer from PTC. So please mark your calendar. I would also like to remind you for the 2024 World Bridge Engineering Conference that will be held in Miami, Florida between December 11 and 13, 2024. The call for abstract is extended until end of May, so May 30th is the deadline for the new deadline for the call for abstract. So please consider submitting your abstract if it's a good fit for the conference themes. And I just want to remind that the conference is co-sponsored by 33 state DOT, including also FWA. And here we can show all the topics in the next slide that can be covered in this conference. And please visit the website for ABC UTC, and you'll be able to also use the QR code here to access the website. And please spread the word and share it with your professionals and professional bridge engineers in your area. With that, I will adjourn this seminar. Thanks everyone for attending, and thanks for the presenters.